Physics can leave you surprised, and at the same time, it can scare you by its laws. But the one who believes in it applies it without any fear. Nigel Stanford, a music composer from New Zealand. He performed an experiment in one of his YouTube videos and put his life to danger. Or rather, we say it like that. Have a look at what he did. He put himself across a very high voltage, but he was safe. The question is, why was he not affected? Well, things always seem typical unless we understand it. So let's understand this. Every charge creates an electric field around it, right? Thanks to Michael Faraday, he told us about this. Now imagine a plain rectangular surface in this field. What is going to happen if we bring it closer to the charge? First, let's mark the initial position, and let's say the electric field intensity is E1 and E2 at the respective points. Very clearly, we know that electric field intensity increases if we move near to the charge, right? So E1 is less than E2, or we can say E2 is greater than E1, right? Now if we bring in the electric field lines here, what can you observe? The surface which is near the charge, or the surface where there is more electric field intensity, there are more number of field lines passing through it, right? At first position, electric field intensity is less, so we have less number of field lines passing through the surface. At second position, electric field intensity is more, so we have more number of field lines passing through it, right? So can't we make up a statement here? The electric field across a surface can be estimated in terms of number of field lines passing through it, right? So we define a term here. Let's say we have this rectangular surface and these are the field lines passing through it. We have a new term, electric flux. This term is nothing complicated but the number of electric field lines passing through the surface. That's it. Electric flux is the number of electric field lines passing through any surface. Alright? Just now we saw that if electric field is more, there will be more number of field lines passing through the surface, right? And in return, there will be more electric flux. So we can say if there is more electric field, or if the electric field increases, there will be an increase in electric flux, right? Now what if we tilt the surface? Well, just by looking at it, we can say that number of field lines passing through the surface has reduced, right? So just focus on the side view, just focus on PQ and see what is happening. Two situations. In one of them, PQ is standing full vertical and completely facing the electric field lines, right? In second case, PQ has been tilted. In that case, the effective length of PQ which is facing the electric field lines is QR, right? Now if we define angle PQR as theta and bring in a bit of geometry here, what we can observe? Let's say the length of PQ is L. So what will be the length of QR? L cos theta, right? And we can say that effective length of PQ while it is tilted, which is facing the electric field lines, is L cos theta. Correct? Now the actual area of the surface is L into B, length into breadth, right? Right now when it is tilted, the actual area or the effective area which is facing the field is L cos theta into B, which is A cos theta. Correct? Now let's bring in some analysis. If the effective area facing the field increases, the electric flux increases. If the effective area decreases, the electric flux decreases. Right? So basically, electric flux through a surface depends on A cos theta, where A is the area of the surface. Right? Finally, we have two parameters on which the electric flux through a surface depends. And what are they? Electric field intensity and the effective area facing the field, which is equal to A cos theta. Now, if we combine both of them, or rather we can say if we take their product, we get a formula for electric flux. Phi is equal to EA cos theta, where phi is actually the symbol for electric flux. Got it? Yes? Now there is another term coming up for us. Area vector. But what is area vector? Or rather the question should be, is area even a vector quantity? Yes, it is. It can be. Why not? Because if we are changing the orientation of the surface, the quantity which we are talking about, electric flux, is changing, right? If the angle of the surface with the electric field lines is changing, electric flux is also changing. So let's define a vector. Let's define a direction of this area. Area vector is actually a vector perpendicular to the surface which we are talking about. The magnitude of this vector is the magnitude of the area, and the direction is perpendicular to the surface we are talking about. Now if we involve area vector here, this is how it is going to look like. And if you are smart enough to apply some geometry, you'll be observing that area vector is actually making an angle of theta with electric field lines. If theta is 0, the electric field lines are parallel to the area vector. Right? You can observe this from the diagram. Now we have the formula. Phi is equal to EA cos theta. What is theta? Theta is actually the angle between electric field intensity and the area vector involved. Right? So can we write it as a dot product? Phi is equal to E dot A. That is how we define dot product, right? The dot product of, let's say, two vectors A and B will be AB cos theta. Correct? So if phi is equal to EA cos theta and theta is the angle between the electric field intensity vector and the area vector, we can write phi as E dot A. Right? Now let's say we have a charge Q and we enclose it with a spherical surface. This is a spherical surface. You can say it as an imaginary surface at the center of which there is a charge Q. Now if we define a very small surface area on this spherical surface, let's say it is dA, this will be the area vector, right? This is how the area vector will look like, perpendicular to the surface, correct? Now how will the electric field intensity look like at the same point? It will be perpendicular to the surface, right? Why? Because in our video of electric field, we have seen that for a surface, for a spherical surface where there is a charge at its center, electric field intensity is radially outwards, correct? So this is how the picture looks like. So can we define a very small flux which is passing through this very small area, right? We can write a formula. d phi is equal to E dot dA, correct? Now if we define infinite number of such small surface areas which can make up this sphere, we can deduce the formula as phi is equal to closed integral E dot dA. What is integration? Integration is actually the summation of infinite number of small units, right? Actually very small units, correct? So can't we add all these electric fluxes coming out of these small surface areas to sum up as the complete electric flux through this surface? Correct? So phi is equal to closed integral E dot dA. Now let's bring in some calculations here. We can write E dot dA as E dA cos 0 degree, right? Why 0 degree? Because both the electric field and the area vector are perpendicular to this surface, and that is why they are making an angle of 0 degree between them. Correct? Now electric field intensity at any point on this spherical surface will be same. Why? Because every point on this surface is equidistant from the charge which is kept at the center, right? So can we bring out E of this integral? Right? We can. What is the value of E as a formula? E is equal to Q by 4 pi epsilon naught R square. Correct? What is the value of closed integral dA? It will be actually equal to the complete surface area of this sphere. Why? Because dA is actually a very small surface area on this sphere. And if we add all the infinite surface area to make up the complete surface area of this sphere, we can write closed integral dA as 4 pi r square, right? Integration is actually the summation of infinite number of very small units. In this case, it is area. So we can write closed integral dA as 4 pi r square. If we place these two in the equation, we will get Q by epsilon naught, right? Now let's bring in the terms which we need. Phi is equal to closed integral E dot dA, which is equal to enclosed charge divided by epsilon naught. And this is a theorem. This is a law which we call Gauss law. And the surface through which you are calculating the electric flux is called as Gaussian surface. A closed three-dimensional surface through which flux is calculated. But there is a doubt. Why we are just considering the charge enclosed by the surface? We have written Q, E and C as a subscript. That means the enclosed charge within the surface. We are not taking into consideration the charges which are outside the surface, because they can effectively change the electric field on the Gaussian surface, right? If there is a charge present outside the surface, it will alter the electric field on the surface, correct? But why we are not taking that charge into consideration? For example, we have a closed spherical surface, outside of which there is a charge Q, as you can see. Now if we draw the electric field lines for this charge, they are going to look like this, right? Now there is an observation. You can observe that number of field lines which are entering the surface is equal to the number of field lines which are coming out of the surface, right? So what is electric flux actually? Electric flux is a measurement of the number of field lines passing through the surface, right? And if the number of field lines which are entering the surface is equal to the number of field lines coming out of the surface, then we can say that net flux due to that charge is equal to 0. Correct? And that is why there is no inclusion of the charge present outside the Gaussian surface in the formula. We just include the charge enclosed by the surface. Alright? But the charges present outside the surface are definitely going to play a role in deciding the value of electric field intensity at the surface. But the electric flux through the surface will only be due to the enclosed charge. So can we write the statements here? Electric field on the surface is due to all the charges present, either inside or outside. But the electric flux through the surface is only due to the enclosed charge, right? So keep this in mind. This is going to help you in the problems. Till now we have been using the spherical surface throughout the calculations, right? Does that mean we can only use a sphere as a Gaussian surface? No, not at all. Will there be a change in electric flux if the shape of the surface changes? No. Actually, electric flux through the surface is going to look like this, right? Whose value is Q by epsilon naught. Now, if we change it to a cube, the number of field lines passing through it will be same as that of a sphere, right? This cube is also enclosing the charge, and that means the same electric flux will pass through any surface enclosing this charge, right? Which is equal to enclosed charge by epsilon naught. But the problem comes in calculations. The problem comes in this part of the equation, closed integral E dot dl. Because for a symmetrical surface like a sphere, electric field is same at every point on the surface, right? But this is not the case with an unsymmetrical surface like cube. And that is why we always take symmetrical surface to apply Gauss law. So Gauss law is applicable to all the closed surfaces, but to ease out our calculations, we use symmetrical surfaces. Alright? Now is the time to give an explanation to what we started with. Let's say we have a hollow metallic sphere. Since it is conducting in nature, charges have freedom to flow, and that is why if a charge is given at any point on the surface, it will be uniformly distributed throughout the surface, right? Because of this, electric field intensity at any point on the surface is perpendicular to it. Now let's imagine a Gaussian surface inside it and apply the Gauss law. What do you observe? The surface, the Gaussian surface, is not enclosing any charge, right? And since there is no charge inside it, the electric flux through it will be zero. Very obvious, yes? So we can write phi is equal to 0 for this Gaussian surface. Now let's expand further. Now I think you don't need explanation for why we are writing cos 0 degree, right? The next step will end up as E is equal to 0. What does that mean? What does that imply? Electric field inside a hollow metallic surface is 0. This is an important observation. This is an important result. Now comes our hero. He has covered his body with a metallic cloth. What does that mean? Electric field inside the cloth will be 0, right? Since it is a metallic cloth. And that is why there will be no charge flow through his body. Since electric field is 0, there will be no charge flow. And that is why he is completely safe. Amazing, isn't it? Now if this video looks interesting to you, just like, share and subscribe and hit the bell icon. For any queries, you can drop a mail at slidescreen@gmail.com.